Okay, today the main topic is Clebsch-Gordon product analysis. This is where quantum mechanics goes nonlinear, and so this is really important. And it's everyone talks about how quantum mechanics is always linear. Well, yeah, if it's left alone, if it's something you can't look at. But as soon as you start looking at it, it's nonlinear, and it's through products, not through input from the right-hand side of a differential equation. So we have a lot of really neat things to look at today, but it is quite complicated. So today, a lot of this that we'll discuss, except for the very early parts of the lecture, will have references to stuff that's lying out there in various places on the hosted machine. That's what it's called now, I guess. Our brand new,
really clear about it.
Giant place that we get to keep all of our stuff, along with the rest of the university. So we're going to take a very simplest possible example of nonlinear product analysis, and that will be really important piece of astrophysics, and that's the hydrogen hyperfine structure. Well, it's one line, a 21 centimeter line that lets us see how much hydrogen there is in various parts of the universe. But just the idea of putting two states in a Kronecker product is the key idea here. And at first you use angular momentum analysis, which involves a Clebsch-Gordon analysis. That's where you take a product of two states of any angular momentum, not just a spin and a half. After you've done that, then you say, well, okay, what if we have another particle or another system? Well, then you need three. And Clebsch-Gordon does not handle three very conveniently. So the thing that we're going to be introducing today is something that was discovered by a British priest, not a priest, just a minister, Alfred Young. Discovered what I call magic squares, but they're called Young tableaus. And we're going to look at the simplest examples of those, and I will be setting the stage for the lectures that follow, particularly the next one, where we look very carefully at not just the use of the Young tableaus for permutations of particles, but also the other side, and this is where we really have to get used to the idea of an inside and an outside. The Mach principle really comes up here, because the other side of is a unitary group.
Dr. Hunter, over there, is it LS to JJ level correlations?
Let me see.
Yeah,
yes.
that one. I think
that's one thing we have to go through. We'll do that rather quickly. As an example of Clebsch-Gordon analysis, where you go from this kind of coupling, where you have total angular momentum, orbital angular momentum, and spin, to where you have, as a good quantum number, the J's, that is the sum of L plus S of two particles. So that's something I want to look at, the correlations. And there's a little misspelling there. I didn't mean to corral the angular momentum, but that's what we do. Maybe this is a Freudian slip or something. But we'll see when we get there. We'll get there fairly quickly. I'm going to go through this stuff fairly rapidly, because our real goal is the stuff that's down here. Okay, let's get started. And let me point out, first of all, these references change a little bit every lecture, and this is the latest until what TC just did a few hours ago, and that will be showing up when you get home. I guess you can just put, or we'll put the whole thing together for
repost.
What's good enough for now, and these will be spread out throughout the lecture, these links take us to other places. Some of them in the group theory lectures, some of them in the lectures of this particular course, but they're also in the textbooks that go with this course, these links. So you can go directly to them, and I'll point them out as we go along here. So the basic idea to start with here, and this is something that we'll do fairly quickly, is to look at products of the simplest case of a Clebsch-Gordan analysis, and that involves, as I said, hyperfine structure. The two spins of a hydrogen atom working against each other in essentially the electronic ground state of the orbiting electron, but also the nuclear ground state of the proton. So it's the simplest, some people would say the simplest case of nonlinear group theory. So, let's begin here. The basic idea, and we've already seen the idea of outer products, the Kronecker product, sometimes the symbol is used to indicate that you're putting together, say, spin up with another spin up, the proton spin up with the electron spin up, the half being a plus number, and then spin down gets first try here with the electron, but not the proton. Then it's the proton's turn to be spin down, and the electron to be up, and then finally both of them down. So we have two states for each of them, and we have two particles. That's 2 times 2 is 4 states. 4, trying to make a linear theory again, but it's a linear theory made out of very nonlinear things, which are the products of the states. So the idea then is we knew how to transform, and we know what the irreducible representations associated with the unitary group of all possible quantum mechanical transformations of spin up and spin down. That's the thing that involves Euler angles alpha, beta, and gamma, and an outside phase sometimes, but this is the case here where we're working with the irreducible representation in unitary form that's standard for quantum mechanics. So the idea then is that we're going to have to take an outer product of this matrix with itself, usually with different parameters for each of the particles, because this system here starts out with a basis that's really a U4 basis. There are 4 unitary dimensions at play here after we put the 2 times 2 together. And this is a rotation matrix that would rotate both. And it's a little hard to see with some of the fine writing, but there's a little E on the betas here, and then next door is the proton P. So the angles that are associated with rotating the electron, and then the angles that are associated with rotating the proton. And I usually draw the electron outside of the proton because the electron's Compton wavelength is far greater than that of the proton. So the proton is kind of in the middle being swallowed by the electron, and those two are going to be independently rotating if you imagine that this system had a symmetry that allowed them to rotate independently. But that would only be true if you had no interaction between them. So this is the case for no interaction, and in all of this stuff I'm multiplying here, I'm going to set the phase, the external phase and the internal phase angles just to 0 to keep the thing simple. So we just have sines and cosines that we're playing with instead of complex numbers. So the interaction now reduces the symmetry. So the huge symmetry that has a 4-dimensional degeneracy is going to be going away. The O4 symmetry is going to be going away because now instead of being able to do that, I have to keep them together. I have to rotate them whatever angle I rotate the electron wave function by. I have to do the same angle with a proton. That's the only one that's going to be allowed in the symmetry that's left after the interaction, which has been going since time immemorial, as turned on. So spin-spin interaction reduces symmetry of this U2 cross U2 to just a single U2. So that's what we have to reduce. We have to reduce this irreducible representation. So what I'm doing here is a little bit of a cheat, but we'll be explaining it much better using the ideas of permutation groups. So I'm skipping some steps here that are usually taken up where we use the angular momentum raising and lowering operators to actually derive what are called Clebsch-Gordan coefficients. So this is the simplest example I can come up with for introducing the Clebsch-Gordan coefficients, which will be a main feature of the first part of what we're doing here today. So by setting the betas equal I then get things that only involve a single beta. We're leaving alpha and gamma off for the time being. But when you put the alpha and gammas back, this is still going to work. What's going to work here is that this thing right here, this particular matrix, is going to be reduced. That is, after I do this similarity transformation with the Clebsch-Gordon coefficients, and you see this right here is a transpose conjugate of this one right here. Well, that's just a transpose. I don't have any imaginary Clebsch-Gordon coefficients. That's something of a miracle that always happens with angular momentum. So we end up here with a 3x3 matrix, something we recognize now. This is something we've seen already. That's the angular momentum 1 matrix right there. And then just a single 1 shows up in the lower right-hand corner, and then 3 zeros on the side and 3 zeros at the bottom surrounding it. So that's what we mean by an irreducible representation, which this would be in the bigger group, is now reducible, and that's the thing that it reduces to. So it's a very simple reduction. That is, we squeeze out 1 dimension, but we're left with 3 for the angular momentum j equal 1. The j equals 0, singlet as they call it, pops out at the bottom of this thing. So here it is in Technicolor. Here's the matrix that we need to reduce. There is a Clebsch-Gordon matrix in the form that you will see if you look it up in just about any textbook that is a reasonable description of Clebsch-Gordon coefficients would display it pretty much like this. Exactly like this if you're high energy physics, and every year the reviews of modern physics would give out a little cheat sheet for the theorists. And it would always include the stuff about Clebsch-Gordon coefficients, including the Clebsch-Gordon coefficients up to, spin 5/2, something like that. That's where they run out of cardboard at that point. So this is exactly the way they would display it. 1/2 cross 1/2, and there are the 4 states right there. And then here we have the things with the total angular momentum 1 for this triplet, which has 1, 0, and -1. And then finally the scalar is this red guy right here. So this is a nice moving wave. This guy's stopped dead in his tracks because it's a scalar.
So the orange one is the singlet state, right, Dr. Hartman?
The orange or red.
Red singlet, right?
Yeah, red for stop, right? Okay, that thing is stopped. But this has got a lot of stuff in it, right? Angular momentum 1's got a lot of stuff. 3 dimensions, okay? So this is an algebraic way of writing. This is a Dirac way of writing it that is pretty not common. That is, most of the time you put the J and the M next to each other. I like to put the supergroup and the subgroup in a supergroup-subgroup chain in a vertical thing when I can. And that's the subgroup chain thing is the thing that makes the tableau stuff work so much better. Tableaus figure out a way to do this very elegantly, and that's what we're going to see a little bit of today. So anyway, and then the same thing I do here, there's the total angular momentum, there's the z component of the electron, there's the total angular momentum of 1/2 also for the proton, and there's its z component number right there. And then they would write C, and often they did write Clebsch-Gordon coefficients this way instead of letting it extend out 3 more spaces. This is typographically much more compact than what you will see in some of the tables that you get.
Can you go back 1 slide?
Say again?
Can you go back 1 slide?
Back 1. What was there? That was this stuff.
Sorry, before that one.
Okay, before that one is the actual matrix and the transformation that we're looking at now. Advantage of the thing that we were just left is color.
I think there is a typo there.
A typo at?
So there is like the Kronecker product between 1, 0 and 1,
Kronecker
0.
product, 1/2.
Up.
Up.
Yeah, there.
1, 0 cross 1, 0.
That one is right?
And then
Look
1,
at the
0,
next
0, 1. Okay, that's should be okay.
Uh,
And then
You might
0,
have been
1,
going
1. That
other
should be
end
okay.
here.
Which one?
yeah, look.
This one?
No, that one.
This one.
Yeah.
1 times the second pair, and then 0 times the second pair.
Yeah, that's correct, right?
Y-
1 times 0
It's
is 0,
consistent
1
with
times
the
1
other
is
method.
Yeah, this goes with this guy. this goes with this guy?
Oh, so you multiply each of this side times all of
Yes,
those,
yes.
and you arrange.
These numbers are the actual
Oh, okay. I
amplitudes.
thought like you multiply all of them times
Yeah.
the number here,
Yeah.
and all of them times the number here.
Yeah.
I was doing it in reverse.
No, this is the actual vector associated with a spin up in the angular momentum basis. Does that make sense?
Yeah, it's like it's
Okay.
like multiplying partitions.
And then this is the little Indian, big Indian stuff that we talked about before when we did outer products, right?
Okay, it's because I was checking in the book too, like as you're
okay.
mentioning. I'm trying because I can see very well there.
Okay.
I'm trying like to check.
Yeah.
Like.
And you know, every time we do a chronic or product of things, this is what it would look like, and it's usually, you wouldn't write it out because you just have 0, 0, 0, 0, 0, 0, 1, right?
Yeah.
And then you have 1, 1, 1, 1, or usually 1, 0, 0, 0, 0, 0 over here.
Yeah, I was doing it the Hebrew way, like I was doing it from left to
Oh,
right,
yeah.
not from right to left.
That's okay when you're got it in a matrix element, but this is the
Okay.
sort of this is the way you'd program it, right?
Yep.
You clear memory for those ones and zeros. Yeah. So that's the deal that we got to get here. This is another Dirac way to write it. Summing. You see, this is a sum. All these repeated indices are getting summed here, and we're leaving the sigmas in. We're not doing general relativity or anything, so we have to do that. As quantum mechanics people don't remember what to sum over if you don't stick the sigmas on there. Right? Okay. So that's the expression for the J-M state, where J can be either 1 or 0, and then the M's have to follow along with that particular thing. Anyway, to make a long story short, what we're going to see by the fact that this thing has broken into a matrix that has J equal 1 and then J equals 0, if it's broken, that means level splitting. That means a projection operator that goes with this, which we're not showing in this case, has split into a triplet. That's this set of lines, and I'm drawing them as 3 lines to show you there, but they're degenerate. They should be 1 level there if you were drawing them really correctly. And then this one is just 1 level as shown. Okay, so what we're looking at is a splitting of this thing by 21 centimeters. Okay, 21 centimeter wavelength of this thing. And this is just a comparison of the observed versus the best job, much better than what we're going to do today, calculated. Okay, and we're lucky even with the best quantum field theory to get this one out to really 5 figures. That's pretty good, and we're trying for better. Theorists are, as we speak, probably working on trying to get 1 more decimal place out of that. But here's the experiment. The experiment is really well known. We're talking about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, but then plus or minus on that. So we're talking about 10 figures, knowing a 21 centimeter line. Okay, and we're getting better at measuring that. Now that's really giving you a precise Doppler shift. That's really important. Okay. So here's a quick way to see how that happened. This is Rokkes Trick for getting energy eigenvalues for the simplest Hamiltonian I can write for this thing, and it's pretty darn good for it. It's just this coefficient that has to be known. That's the hard part. But just to use that, we've got J proton, J electron as a Hamiltonian with some coefficient. Then I do this little trick here that Jp.Je is equal to Jp plus Je squared minus the diagonal, the J squared, P squared, and E squared, okay? But I've got eigenvalues here for this. This is J total here. I know whatever the total angular momentum J is, I put that's eigenvalues down. And then I know the eigenvalue for each of these guys. Each got a half a spin. So you're going to be getting 3 halves times 1/2 is 3/4 for each of those. So when you're done with that, J equal 1 gives you this, and J equal 0 gives you this. And that's what we plotted. So you'd say, we're done with that problem. But Not quite. Okay. First of all, there's all the argument about the parameters and what's involved in them. And this is called the Fermi contact factor, the factor of this thing, is that's the name that's given to it. And there's a little bit of the theory behind this in the links that I'll point to in just a minute here. But anyway, the important features of it, the Bohr magneton, the gyromagnetic ratio, all of that kind of stuff, eventually the G factor, the gyromagnetic coefficient, all of this that gives us the coefficient here, which is 1 over 21.1 Kaisers. Kaiser is an inverse centimeter. Okay, very important spectroscopic unit. So there's your all of the physics that we know going into that. And of course, the calculation of the things that go into it, as I say, is the really hard part of this. All right. Anyway, the matrix part of it is kind of interesting. That we can quibble about and work with very easily in just a few minutes here. First of all, I can write the Hamiltonian in the basis of the products. That is, proton, electron, both up. Proton up, electron down, then the other one, and then finally down, down. That's a 4x4 matrix. It's all diagonal. Okay? If I don't turn on any fields to make this thing move, if I don't turn on the interaction between the proton electron, excuse me. This is the case down here where I have no magnetic field, but when I use my Cupps-Gordon basis that's all coupled up into angular momentum 1 and total and 0, I see here those eigenvalues, the triplet 1, 2, 3, and the singlet in the negative region. That's kind of the whole story. If I just have the interaction on and no magnetic field, or if I turn on the magnetic field and for some reason there was no interaction, the interaction is obviously going to be making matrix elements out here. And for this one, the magnetic field is going to be making matrix elements out here to do the Zeeman splitting of the triplet and then moving around the other eigenvalues of the singlet as well. So that's the thing we want to look at, okay? And of course, that's the key to connecting these two. So, using the Clebsch-Gordan coefficients, we go ahead and we write the matrices for the whole Hamiltonian that includes both the interactions and the magnetic field for, first of all, the initial basis. And we get a little 2x2 matrix here that mixes up, down with down, up. That's not too surprising. And then we get the 2 up, up, and down, down, actually showing there with the same energy. Then the magnetic field can go and work on that. That means you're going to add all of these coefficients here to the diagonal, and you'll have a avoided crossing of levels, which we'll show in just a minute. Here's the other way of looking at it. If you use the Cupps-Gordon basis right away, you'll discover that the magnetic field is off diagonal just right there. Okay? So together, these things tell a story, and there's the story. This is for a weak proton moment, which is kind of what we have. Proton moment is down from the electron moment by roughly the ratio of masses of the electron and the proton, which I think I've already said in these lectures that that's pretty close to 6 pi to the 5th. It's around 1800, okay? And to 4 figures, it is 6 pi to the 5th. And as I told you, there was a guy that came to Caltech that said he had derived that by group theory. He had not. He had just been lucky. And he had gotten a bunch of other constants too, so it looked enough like he had something, and we were very disappointed when he didn't. Yes?
What is ESR translation? ESR, what does ESR stand for?
Okay, as you go back and forth between the electron levels, you see this is the case here where all the electrons spin up. This down here is all the electrons spin down, right? So what we're talking about is a beating between those two roughly, and that will be electron spin resonance.
Oh, okay, electron spin.
That's a short answer, right? Okay, and then NMR you probably already know, nuclear magnetic, that's the proton at work. That's what you're talking about right here, okay? As you turn the magnetic field that varies a lot, okay?
Aha, that's cool.
And if you don't have your magnetic field, then you're here. But then nothing works if you don't turn on the magnetic field, right? If you're going to take images of people and you don't have a magnetic field, you can't charge any money. The Earth's magnetic field is not going to do it for you. Now, as you make the proton moment bigger, this changes a lot. These two, remember, there's two levels that are just linear in the field, and that's what we've got here. But here, the linearity is such that they cross. And this isn't often shown in descriptions of this, but that should be. This is with a medium moment. And then you can make it really screwy. There's all kinds of things that you can do with problems that involve this kind of two-level system mixing. And also, and I want to point this out, this if you click on this link right here, okay, you'll get the end of the deeper theory. That's in chapter 24 of Unit 8, I believe. And well, let's just take a look at what we get just for this. I'm feeling brave here, so I'm going to bring this guy up to speed and go ahead and click on that and see if it brings anything up that's reasonable. But I've put these things throughout this particular lecture because we're going so many different directions now. It would really help to be able to see it. So this is the first page right here, I think, of a better hyperfine theory where we just go right back to the Hamiltonian A dot P. That's mainly what we work with, but the other stuff's important too. And this lets you, if you're using Foxfire, you automatically get a nice page showing thing here that gives you this. And at the end here, I describe this crazy business. This is my picture. If the electron had an electric dipole moment, then this would be relevant. And people are looking for the electrons or nucleon dipole moment in the E department, not finding it. So this is just to show you what the fields look like if you did have an electric dipole moment of the proton, okay? And we imagine that maybe the electron had it too, okay? So you would be seeing the usual thing, and inside there would be separation of charge. And that's a microscopic view of this, okay? So at the microscopic view, that's what's going on right in the pixel that's underneath my finger there. But if you're talking about a magnetic dipole, that's a whole different thing. There's nothing, nobody's home at the center of that. Okay, at the center of that, we've got some kind of current loop, okay, that the electron is producing, having swallowed the proton, which also has a moment like this, but much smaller. Now, what's true about the electron is that its actual momentum, spin momentum, the little arrows here, points opposite to the magnetic moment, okay? So the magnetic moments is what I'm showing here, and that's what you'd see, but this is showing how the proton interacts. Proton has a core like this, but so does the electron. So the idea is, how do they talk to each other? Well, they just talk with J dot, JE dot JP. So this is the Fermi contact term. But that Hamiltonian description gives you a whole bunch of other stuff too. And that's interesting for other reasons. As you start to pull these apart and as they start to orbit more and all that, all these things come into play. So this theory gets really hairy. But you know it's there. Okay, let's go ahead. I'll take this one back home here because we need the screen for other things later on. I'm going to go ahead and let's see if I can get this thing to shoot. There we are. Okay, so I can go ahead now and do the next thing in order of the mathematical description today, and look at something where we have not just 1/2 cross a half, but let's do 1 cross 1. Okay, that gives us a lot more states. We've got 3 cross times 3 is 9, different possibilities here. 1, 1, 1, 0, and 1, minus 1, and then we've got 0, 1, 0, minus 1. Those are actual angular momentum numbers that are appropriate for a spin 1, or orbit 1 is what we'd usually be doing this for in atomic physics. Okay? And then our Clebsch-Gordan coefficients sit in a square table that looks like that. And again, this is something where you would stop in an ordinary quantum mechanics class, get out the raising and lowering operators and figure out these coefficients from various arguments based on them. I'm skipping that because we've got better ways to do that today and days that will follow. But in any case, if you were to draw a level diagram for this, what you would see is, first of all, when the angular momentums add up, more or less by being in parallel, you get 1 plus 1 is 2. And that 2 is represented by a D for angular momentum 2, diffuse spectra, the ancient notation of spectroscopy. And we get both, and this is weird, all spectroscopy, including nuclear, molecular, and atomic, puts the spin as a superscript on the left-hand side, but they don't put the spin there, they put the multiplicity there. Well, that's really honoring the experimentalist who's going to be looking at this thing, and he's going to see a singlet when he puts a magnetic field on for those 3, and he's going to see a triplet coming out when he puts a magnetic field on that's strong enough to split the levels of these triplets and these singlets. Now the deal, of course, is, and this is a reference to a verbal description of it in chapter 24 of Unit 8, this is what you get to have if the two angular momentum 1, that's P for principal, the ancient notation for angular momentum 1, when the two principal electrons have different radial quantum numbers, you can do this. But you can't get all of those levels if it's a P squared. And it's the same P, same radial quantum number. This one, you lose 2 of these, and you lose just 1 of these. You lose the P1, you get to keep the S1, and you get to keep the D1, and then this guy, you lose that, and you lose that. So that's something we've got to see. What happened? Why did we lose this guy? This is blank now, it doesn't exist. This one, nothing there, okay? Assuming everything else the same, okay? And in particular, assuming these have the same radial quantum number, which of course would change the whole energy picture, but I'm doing it in a funny kind of way here.
Can you just go one step back?
One step back
Yeah.
is this guy.
Yeah, so I think there's a typo. It's page 14, not 17. This figure is it's on page 14.
Okay.
Chapter
Of
24, page 14, not 17.
Let's
See if
take
the
a
link
look.
takes us there. Is
Let's
it mine
take a look.
actually?
We might as well go there.
I mean, I'm just looking at your...
Yeah, I definitely want to get that. I spent a good part of this vacation cleaning up a typo that Lewis found, which was 2 I1s, or no, was it I2? 2 I2s in a group table for C3. And this is, we've used that for a long time and nobody discovered it. So I'd go back through all the literature to try to get that fixed. Let's just take a look, see if I can get to that point right here.
It's 15.
14 is right here.
14, yeah. Oh, okay, so I guess, so I'm just...
14 has got this thing, right?
Yeah, and
And
then
then here's the picture of both of them,
in 15.
and that's 17.
Oh, okay, 17 on the...
Yeah.
Oh, I'm sorry, the 17 on the PDF
Yeah.
file. Okay.
Yeah, and then these are the actual states and all that kind of stuff,
Oh.
which we're going to discuss right now.
Oh, I'm sorry. I was looking
This
at the chapter number here. It says 14. Oh.
Oh,
my-
okay. Well, whatever it is, write it down. We'll track it after
Please,
class.
especially if it's a chapter.
Yeah.
issue.
Yeah.
Dr. Harter?
Yes.
So if I found like typos in the book, should I also tell you?
Oh, heck yeah.
Okay,
Yeah.
because I have found.
I've got a list somewhere already, but
Okay.
I've had so many arguments with Wiley Underscience as they went out of business. They got
Do us one
eaten
favor.
by Elsevier.
In the subject, mention what source you're talking about.
Yeah.
If you're,
Yeah, make it a
whether it's the
record that we can-
website or whether it's
Should be able to fix it.
Symmetry Principles or
Yeah, I don't do the website, I do the book.
Yeah.
It's because I like the book better.
Okay, now let's just take a quick look here at the way we write these in using quote unquote modern notation of Young tableau. Now, Young tableau is 1800s. Okay, so it's a lot, and it was by a guy who didn't know any physics, and of course this physics didn't exist. So, you know, it's one of those things where you discover something and just kind of looked useless. But now I'm seeing it as a really incredibly powerful way to handle multi-particle things. But this is the way that I write the things when they are symmetric. That is, if I take a combination of 1, 0 and 0, 1 with the square root of 2, I just write it that way. And we'll get into this, making this formula, but and I do the same with that one down there involving 0 and minus 1. I put the minus on top of it just to keep everything within these boxes. Okay? And then you come over on this side and it's just the opposite. This is anti-symmetric. So we put the numbers on top of each other to indicate that. That's the great big deal of Young tableau, sort of exposed for the simplest case, two things. But the power of the Young tableau is that it goes beyond just the marriage of two. This allows you to have a ménage à trois, a ménage à quatre, whatever, any number of particles all put together at once. You see, not in sequences that are very confusing. And then once we get over here, it's symmetric again with respect to 1 and minus 1, but it has a coefficient that's different from the 0 one right here. We had two things in that one, so you get an extra square root of 2 there, which you don't have there, but this one has a minus sign on it. So that's the notation that we're going to have to get used to. Just a glimpse of it right now that I want you to see, okay? But the main idea of it is once you've put those combinations of orbit together, then you also do the same thing with the spin. And here's the notation for the spin a half that we just coupled recently here. And when we coupled them up to 0, that was the very far right-hand side of the Klipsch-Shorten table, we had an anti-symmetric combination. So I put spin up over spin down to indicate that. And that's who's going to get to live with the symmetric states. Whereas this anti-symmetric guy here, that's the big P, is going to get to live with a triplet. And it has to live with this triplet. It can't live with this singlet. So there are the four states broken up into triplet plus singlet of the spin a half. And there's their notation right there here. This one with only one term, this one with two terms, so you get little coefficients that indicate normalization. But this is the actual wave function written in Young tableau ease. And you see the orbital part is anti-symmetric. The spin part is symmetric, so the whole thing is totally anti-symmetric. That's what Pauli and Fermi demand. That's the Pauli, Fermi, who else? Dirac symmetry, okay? Selection rules require total antisymmetry for these wave functions because we're dealing with fermions or Paulions or Diracons, right? You're talking about a spin a half thing, okay? So you have to obey these rules. The whole wave function has to be put together in that fashion. Now here's the singlet, this guy right here, the orbital singlet. I said angular momentum total 0. It's going with a I'm sorry. The orbital singlet here, this S, is going with a singlet of spin. That's the very top level here. That's the one that makes a symmetric combination of the electrons. So they're really forced to live together very close in this, whatever you want to call it, relationship, this sort of double relationship here. And because of that, their repulsive electronic potential energy is very high. So you end up with this guy on top. But the triplet that's just the opposite here. When you talk about a triplet, that's this guy right here. Then the orbital part is antisymmetric. So there's zero probability that they're actually on top of each other. Where the largest probability is that they're going to be on top of each other there. So this is where the triplet gets to be low energy, low electrostatic, so-called exchange energy is low for that one. Then this thing in them, this guy here is kind of stuck in the middle, okay? But this and this are forbidden. So that's what the Pauli, Fermi, Dirac selection rules do, and then there's the Einstein, Bose, and I don't know if there's another person I could put on that, maybe Boltzmann thing that goes with bosons. Bose is the name that stands out there. Fermi's name stands out for the fermions. Okay, and that's what we're dealing with right here. And for most of our nuclei and our molecules, spin a half is pretty much what you see all the time. Hydrogen, starting with hydrogen, okay? But sulfur hexafluoride, fluorine, spin a half. Chlorine, usually spin a half. There's some isotopes that's different, but that is pretty much what we'll be seeing in molecular things too. Now, Young tableaus for orbits. Here's what we ought to learn about in the next few days, is that there are things that are not totally symmetric or antisymmetric. They're sort of half and half. This is called an octet. That's a octet of the U3 theory for particle physics. But for us, it's the P level of nitrogen, which has 3 electrons fighting it out with their symmetry. And then, of course, the triplet singlet, you can understand that one pretty easily. These would be called quarks in high-energy physics. Here they're the antisymmetric triplet that we just put there. And then here's the symmetric triplet that we put here. And what's in there is the scalar orbit, as well as the 5, 1, 2, 3, 4, 5 states that make up angular momentum 2, 1, 2, 3, 4, 5. Okay, so this is just a glimpse of the Young tableaus at work for not just 2 particles, but when we do 3, it'll be just as easy to work with that as it is to do with 2. That's the beauty of the Young, one of the beauties of the Young tableaus. We're trying to try to show some others fairly shortly here. Okay, now at this point I want to mention that we haven't really derived these coefficients. We're waiting on this. Okay, so this is where, and I'm not going to click on this right now, but this is the start of the discussion of the derivation of a formula that's very much like the formula for the D functions, and it in fact uses the D functions to produce something that's quite similar in some ways to the Wigner irreducible representation D functions that we use for wave functions for our rotors, but also central column. We use it to get our harmonics, remember, the spherical Y harmonics and all of that. All of that stuff is in the D functions, but this is putting them together with each other. And that's what we need to learn to do skillfully here. Anyway, clicking on that yields the beginning of that formula derivation, which I'm going to skip right now. But here I want to just sketch something that is in every modern physics class, the idea of what kind of coupling you get for the 2p squared, that is the same radial quantum number, but if you have different radial quantum number, then you can get some extra states that are indicated by dashed lines here, okay? And then the ones that are allowed down here also indicated in red, sort of they get thrown out for this case, but they get to live in this case where the symmetry, radial symmetry is different. So that's a key thing. And this, the discussion of this, click on this and it goes to that discussion. That's on the same basic area, Unit 8, Chapter 24, page 22. is what should come up on that click. Now I've put those links together fairly quickly, so I wouldn't stake my life on them all right now, but you can try them. We just downloaded this thing, so you can actually try it right now if you pick it up on the web. Okay, here's something that's interesting about this. I'm going to go through this fairly quickly, and this involves something that's really important for the physics going on in this building, where you're looking at the magnetic properties of various elements. And the thing that's key to there is to how much magnetism you're going to have is Landa's gyromagnetic factor. So clicking on that, which I will do in just a minute here, is involved here. But here I'm thinking of a lot of angular momentum crossed with maybe a lot of other spin angular momentum. But this is also the kind of diagram we'll use when we put our molecules together with vibrational angular momentum. We've done the rotors already pretty much, but what happens when there's something on board? Like nuclear spin, that's also going to make a diagram that starts out something like that. Okay? But here's the amazing thing. When you do that, and you draw a picture using angular momentum cones instead of just little arrows, okay, you get something that's really quite amazing. This is an actual plot of Clebsch-Gordan coefficients for angular momentum 9 cross 9. Okay, I think that's what we use. Let me go one step ahead here and see what it is. Yes, 9 cross 9 to give 18 gives you a little Gaussian-looking lump. Sound familiar? Well, we had the D functions, right? But this is a very different context. I have here something that only lives really with high amplitude wherever the classical picture of the angular momentum cones ends. In other words, the inflection point for that Gaussian-like dot collection is right underneath there. It's right about there. Okay, and the same one for this one. This one has an inflection there and there, but now 9 cross 9 to give 17 has a node in it. And then this one has 2 nodes. And since we don't have very much angular momentum here, we were doing it with 20 with D function. This is just 9. Oh, that's adding up to 16. But as you go through and make less and less, you get what looks like chaos for the distribution of the dots. But they start out with what looks like harmonic oscillator functions that have been translated. If you've got the angular momentum total J down here, this is 9 cross 9 to a component of 5 instead of 0. Okay, I move this thing over to -5. That's where the peak of the thing is, but it's still got a inflection points that go from there to there, according to the cone diagram. So this is kind of a picture that would look like if I did this with 20 at the time I first did this. I didn't have something that would plot Clebsch-Gordans that well, but here you really see it. Okay, there's the very many turns of this particular angular momentum for cone. This is just a sketch, but I think it's just a sketch. I may have actually done that one. But anyway, that's what I wanted you to see, just to give you some idea. And I also wanted you to see how the Lambda G factor works. And that's this picture here. And so clicking on this gives the description of how you calculate the Lambda G factor. It's a pretty easy thing to do, but it involves a little bit of thinking about what the physics is doing here. If I didn't have any coupling between those two angular momentum states, I just have these guys doing their thing independently with respect to some D axis that was defined by a very weak magnetic field. But if I get the thing going here at precessing, even if the precession is slow, and it better be in order for us to have L and S be good quantum numbers, then I get a picture like this. And this lets you actually figure out how much magnetism is available to you for a given atom, that once you know its shell structure. So I recommend this is something to learn. It is easily done at that point. It's not something we have things like this to do with molecules, but I'm going to skip on from that. Okay, now here's where we take the simple elementary marriage, the pairing of two angular momentum states, and say, hey, let's get them a non-Jetois, let's get 3. oh, 3's good, 4's better, right? Okay, we're just throwing tradition to the winds here, right? We're going to have 5, 6, 7, 60 spins. That's what we're aiming at. If this project works, right? We're going to be able to look at the hyperfine structure of this monster molecule, okay? And it's going to have a lot more than that, 1/2 cross 1/2 cross 1/2. Now, that's pretty easy to do, and I like this notation better. Some little d function to the 1/2, okay? And the crossing of 1/2 gives us a singlet plus a triplet, right? So that's kind of what we're doing with the Young tableaus down here. We're saying, okay, I've got 2 Young tableaus, 1 spin up, 1 spin down. That's for the case of a 1 particle system, but I've got now 2 particles, okay? Particle number 2, okay? So I'm going to have a dimension, that's a little L there for dimension, and it's a group theory dimension, L of a certain tableau, namely the one that's 1 over 1, the antisymmetric guy. And then there's another tableau that goes with C2, also of dimension 1. It's called 2, 0. That means 2 and then nothing else. But for spins, I can load that thing in a symmetric fashion with them to make a triplet. So here's my singlet, here's my triplet. Okay? Now the idea is we're gonna take it out to about there. All right? We're gonna just keep adding an extra spin and a half to that. Okay? Let's do it up here algebraically first, because there's the diagram. But we got 1/2 cross 1/2. That gave us a 0 plus 1. Cross a half, so now I've got to do a 0 cross a half. That's pretty easy. A scalar cross a half. I just get a scalar right there. End of story. But we've got this other guy here, D1 cross 1/2. Well, if you remember your Klutch-Gordon way of thinking of these things, you know you're going to get 1 minus a half, and then 1 plus a half, and that's it. You're going to get a half and 3 halves out of that, and that's as much as it's going to go by the rules of the quantum. And that means we're going to have 2 of these halves and 1 of the 3 halves. Okay, how does that come about? Well, we're talking about 2 spin a halves, and here they are, both of them. Okay? Spin up and spin down. Both of them attached to antisymmetric combination of paired spins, which is essentially no spin. But the Young tableau tells us, well, that's what you've got. And you'd better use the number 2 because that's the dimension of the irreducible representation of this particular tableau. And that's what we've got to learn about. We've got to learn about how that works. Okay? Now, here I've got 4 ways to fill a symmetric tableau whose dimension is 1. This is going to be like the A1 representation of the group S3. And this is going to be the E representation of the group S3. We got 3 particles here. Okay, so that's, you see, already we're taking care of something that's pretty complicated. This would be a mess with Klutch-Gordon coefficients. Not a terrible mess, but much messier than what you get with the Young tableau analysis as you get good at it. Now we do it again, okay? This time, basically, I'm going to put 4 of them together, so I can cross it this way if I want to, or I can cross it this way, okay? Anyway, after you filter all these down here, you're going to find you have 2 singlets now, 3 triplets, and a partridge in the pear. No, that's not the way it goes, is it? You've got 1 angular momentum 2 here. Okay? 1 is the, now talking about a tableau that goes with the A1 representation of our octahedral group. Actually, tetrahedral group is what's behind this, but they're isomorphic, so we can use the names anyway. And then 3 of these. This is going to be the T2 representation of the tetrahedral group, or the octahedral group that we've worked with so long. Its dimension is 3. That's where the 3 comes from. And then this one down here, this is kind of weird. This thing is the E representation of the octahedral tetrahedral S4 permutation group. 2 of them. That's where we get the 2, right here. Okay? That's what we're aimed at. We're aimed at understanding the arithmetic that is so powerful from these tableaus. Okay? And for people in information theory, I'm just amazed that they aren't just using these things all the time. There's got to be a way to get some insight for systems of that nature. Here's where we stop for now. This is the icosahedral dimensions here that we'll see fairly shortly, okay? But it's the same deal, the same basic idea for these things. And each time we're using Clebsch-Gordan coefficients on top of Clebsch-Gordan coefficients to make a tableau that would go in this diagram. Now let's go ahead and just blow this thing up, right? Make it really kind of big to this. And here's a couple of links. This is introductory to the 3-particle thing. This is introductory to 4-particle. And this is just a little bit of the magic formula we haven't looked at yet, but they give you all the characters and dimensions that we'll be talking about later on. Today it's just sort of magic formula, okay? Now I'm going to bring this guy up so I can show you the magic formulas. That's the spectacular part of the Young tableau analysis. Rather than look for it in there where it isn't, I'd better take this guy back home and bring the actual lecture up to speed so that I can be, assuming it's all going to work, that our links are in good shape. There we go, okay? And in particular, I'm going to be interested in this guy right here. So I'm going to have to click on the chalk tray over there to get the formulas that give you the various things. Now, one of the things maybe that I should do before I do the magic formula is actually show you how the connection between, I'm sort of glib here about the connection between octahedral, tetrahedral, and trigonal, and then of course this is more obvious down here when you have only 2, but right here that's already quite a jump to realize that you're actually dealing with A1, T2, and E representations. Why is that? That's a little bit of a stretch. And so maybe what I should do here is go back and look at the intro to these. Now, this is a little bit of a stretch. This will be showing you just where the connections start, and this is what will be one of our main slides for the next lecture, but just take a look for a moment that it looks like what I'm saying is true. Here we have the representations of the permutations, and we're going to have to get used to that notation. That's called the partition representation. But so is this a bunch of partitions. In other words, the idea of summing numbers to get 4, 1 plus 1 plus 1 plus 1, and then so here this particular guy, the E right here, is 2 plus 2, and he has 2 states that look like that. The A2 is just totally anti-symmetric. This is totally symmetric, so that takes care of these 2. But then the E, that's this guy right here, has 2 of these tableaus. The one that we're looking up over there is partially anti-symmetric but partially symmetric. That's the T2 that we're talking about at the very bottom of that table. We don't get to use this one because we don't have more than 2 spin states. This would work if I had spin 1, and I'd get to be able to put 3 different things in the columns. Remember, this has to be totally anti-symmetric. This has to be anti-symmetric. Anything that's up top it has to be anti-symmetric. This is quadrantly anti-symmetric. Okay, we can do that with numbers 1, 2, 3, and 4. We can't do that with spin up and spin down. We run out of gas right here. So we get to use that one, but we don't get to use that one. We do get to use this one because it's only got 2 rows. Okay, so we get to use this one, and this one, and that's what comes out right there. Okay, so that's it in a nutshell. Just to give you a feeling for the incredible power of the just laying it out, not actually calculating the numbers yet. We'll do that in a minute. That's the magic formula that I want to show you that goes with this. Okay. Now, it may be that I can just go ahead on this one, that is, work it up to a point where the magic formula I show. That's one of the magic formula. That gives you the irreducible representations of a state labeled by tableaus. Kind of a weird tableau that looks like somebody's T-square. But here's the formula that really swings. And we're getting the dimensions of the representations of both the unitary and the permutation. And they're intertwined. And there's a reason for that intertwine. It's called Mach principle. But the basic idea here is that if I need to find the dimension of a tableau dimension, that is a permutation dimension, I put the numbers n factorial up on the numerator here, and then the tableau is assigned hook lengths. That is the number of boxes in a hook. A hook is horizontal plus vertical, so 8 is here. That's 1, 2, 3, 4, 5, 6, 7, 8 goes right there. This one is 4 because it's 1, 2, 3, 4 in the hook. This is just 2 in the hook, okay? So putting those hook lengths as a product down there gives me the dimension, say, of our favorite A1 of S3, 3, 2, 1 times 3, well that's 1, okay? Same thing here, 3, 2, 1, now it's 3, 2, 1 going down the side. But this one, okay, it's 3, 2, 1 divided by 3, that's 2 times 1, that's the dimension of the E. So you remember it took us a little bit of time to get the number of dimensions and the characters of S3, right? You get them instantly here for huge groups. So that's why I call this the most powerful mathematical notation that's been discovered in mathematical physics. And it's just starting. We're just scratching the surface of this amazing thing. So if I go down to the end here, you'd figure, how am I going to get the numbers for that? I don't want to do all this multiplication. Well, the numbers make a funny triangle. I could do that and then just give you the number. But here's what you do to get the U2 dimensions of this thing.
Dr. Mark, there's a typo there. 2 to the power A is 256.
Let me point.
Oh, yeah.
Here?
The 2 to the 7, 2 to the 8.
To the right, far right.
Right.
Far right.
Yeah.
Next one, to the 8 is 2.
Copy and paste and not yes. It's 256.
Yeah.
Yeah. Another one. Got to get rid of that one. And that's a lot of places. So we got to get rid of that one. Yeah. So we're talking about 256 here. We're talking about 128 here. And the thing is that every time you get a 2 to the nth, you've got to sum that's the sum of the products of these two dimensions. One for the tableau, one for the spin unitary 2. This is unitary 2 dimension right here of angular momentum. It's the 2s plus 1. Okay? And then this L bracket, okay, in terms of giving you mu1 is that length and mu2 is that length. Okay, so you have to do a little geometry of subtraction of the blue squares from the reds, and what's left over here is the number that determines whether it's a singlet, there are no reds, it's a triplet if you have 2 spin-a-halves, and then if you put here 4 spin-a-halves, you get angular momentum 2, which is a quintet, right? 5 states for angular momentum d orbital 2, and then if you go up here, you actually have angular momentum 7, okay, dimension, you have angular momentum 3 there. So 3, 2, 1, 0. Add up those multiplicities times the tableau dimension, and you've got 2 to the, whatever the particle number is there. 2 to the 6 is 64 is what you get with that. But this thing is giving you the formula for that particular dimension, and all the numbers are the same according to this, and so it's 1. This is telling you singlet for this one, okay? But the Sn dimension is not a singlet. The Sn dimension is, this is 8 here, 8 factorial divided by the, and this is what's happening in the denominator here, are the hook lengths, okay, all product up. Well, most of them cancel. What you're left with here is a 7 times 6 over 4. Okay? That's 14. That's what shows up right there. Okay? There it is, worked out in completion. So this one's giving you the fact that this is an angular momentum singlet down here, and this one is telling you, yes, but there are 2 times 7 of them, that's 14. So, that's magic. That is amazing. Okay? We value magic here. So nature's got horrendous amounts of magic. If we can get a little bit of magic, we might have a chance. Okay, that's kind of the rule of our work here. Now, when you're introducing unitary, we've already done this with the oscillator. It's pretty easy as you go to higher dimensions of oscillators to get the numbers that represent their dimensions. It starts out just being stacking numbers, or triangular numbers and things. So if you're willing to work with just symmetric states, it's pretty easy. Remember, we had bosons, so you don't have to go too far. But we don't stop there. We start having these guys very early on in our analysis of our angular momentum 1 states. There's 3 of them, and damn it, that's a U3 problem. That's the most elementary U3 problem. The most advanced U3 problem, of course, is Gelman and Zeeman and Zweig doing the quarks, or as Zweig called them, the aces, that gave them the theory for the omega minus particle. Just one lousy particle in all of the spectra of the high energy machines of the day was understood, quote, understood, by just that kind of arithmetic. The 8-fold way, and then the 10-fold is not shown here, but there's a big triangle that comes just on the same level as this 3 triangle that gives you that. We are happy to be able to do atomic physics, the old-fashioned atomic physics with us. Now, the way this is going to work, and this is something I'm just warning you about, is once again the Mach principle is going to come in here. We won't say much about it at first in the next lecture, but it's there, and I'll point out where it's hiding. But the basic idea is here, we're going to label some sort of body or particle A, B, and C, just so we don't have the same label as we do for the actual states in which those particles will go. So that's the game we're going to be playing here, is we're going to have operators that are defined by what the particles are doing with respect to each other, and then we'll have another game that's completely equivalent to this one about how the states can be moved around, and in both cases it's possible to linear combine. These don't combine very well, except in nuclear physics, where you can transmit a proton into a neutron through beta processes. But most of the time when we're talking about an electron doesn't like to change into anything else, so we'll just be doing permutations of the electrons. But over here we're going to be taking linear combinations of the states, so that makes this one sort of the unitary side of it, and this the permutation side of it. But they can both be unitary side. So that is something we should be aware of possibly happening. So we'll get into that next time. Now, I want to finish fairly early so we can stop and have some questionings about what we've just seen, and maybe look at some of the links a little bit. But I would like to go into now the real other nonlinear part. I was promising all sorts of nonlinear today, and going to try to meet that promise by talking about the tensors that we've been building during our little exercises here. So I want to see a little bit about tensor operators. First of all, with spin a half. But there, it's called a vector operator. A half cross a half gives you a vector, not a tensor. You need angular momentum 1 to pull out the first second rank tensor, right? So let's start really easy again, like we did up here, with just a half cross a half. But this time, and this is the weird thing about this is the link right here where it begins, page 5 of that chapter 25, the irreducible representation tensor building that I'm going to show you. Because this is the other way to think about Clebsch-Gordan coefficients. There's something called the Wigner Clebsch-Gordan expressions for the tensor, that involve Clebsch-Gordon coefficients, but that goes along with the derivation of the Clebsch-Gordon coefficient. So we're trying to come at things from a couple of different directions here, and that is something you're going to have to sort out. But we're all already very familiar with a linear combination of a Hermitian Hamiltonian with our old friends sigma x, sigma y, and sigma z, or as I like to call them, sigma asymmetric diagonal A, bilaterally balanced B, that's x in the normal, for normal sane people in physics, and then here is what we call the C, curly centrifugal complex blah 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 blah, that's y, right? So we spent a good amount of time doing that, right? And that's a whole theory of ellipsometry, right? Amazing, really powerful spectroscopy. And then all the two-level systems come along and they make use of that too, right? So here I'm going to call them irreducible tensors. Now I'm going to combine the x's and y's. It's going to be x plus iy is x minus iy with a phase. And coefficients then have to combine too. So I'll be talking about the b minus ic, and I'll be talking about the b plus ic, the off-diagonal matrix elements of the thing that started this. And then there's this guy right here, just plain old T0. So there's really 4 things here, but only 3 of them are really doing anything. This is a unit operator. Okay? So it starts out as a U4 thing, because it's, you know, we're doing it nonlinear. We're making products out of this thing. So really most people would just look at those right there. Irreducible rank 1 vector and a rank 0 scalar is all you've got. Forget about this guy. Everything's being done by that. Well, not in information theory. This thing's the one that's screwing around with your phase, right? And I'll have to worry about that. But that's why we have 4. Okay, now this is what we get with angular momentum 1. We get the 4 that we already have here, but now they're 3 by 3 matrices. We get a whole number 5 of rank 2 tensor. So there's your first healthy rank 2 tensor object. And you know what's coming is the next layout here. This is quadrupole. We're going to have an octupole on top of that when we go to 4-state systems. And so on. Okay? So now you see this tensor building is really important to modern physics. Has been and will be. It's important to see that. Now, how do you do the building? Okay, well, today we started out by doing hydrogen hyperfine 21 centimeter analysis with kets that represented spin a half. Spin up, spin down, spin positive a half, spin minus a half. We put together the states, symmetric combination of them, and another typo, the anti-symmetric. Well, it's not a typo. The minus one is hiding right there. Okay, it should have been better exposed. It's only taking out 2 pixels. We've got to fix that. It's not a mistake, but it's bad form. Okay, so here's the scalar singlet. There's 1, 2, 3 triplet made out of symmetric combinations. That permutation of those two doesn't change it, whereas the permutation of those two was a minus sign. That's the key Young tableau analysis of these two. Okay? We can do the same thing with this. Only now it's not going to be kets and kets. Okay, there's a ket. There's a ket, right? That's what we got over here. Okay? What we got to do over here is put them knuckle to knuckle. Okay? We're going to do the same thing with combinations symmetric with a minus sign. That's the rub right there, is that this little -1 to J minus M phase has to be stuck in everywhere in order to make that work over here. So that's a little fly in the ointment. This is why angular momentum calculus is so roundly hated, as it has things like this. It's so and you get all done with a huge calculation and you drop one of those and it's completely wrong. So it gets a bad reputation after a while. Okay? Young Tableau doesn't have that problem, but let's go on. Here's a symmetric combination right here. Well, it's not quite symmetric. It's got a minus sign right there, right? Just like this guy down here had a hidden minus sign right there. Okay? That phase is really important. If you leave it out here, well, what am I making the wrong kind of scalar? But that's what we got right here. Okay? Now, the deal is, of course, that this is going to be an overall phase, so that this is still a unit matrix. It's got a minus sign outside. And you see this is in brackets. Okay, this is the new guy right here. This is another way to describe the three guys that we have here. Okay? And we line them up in a triangle, just like the previous slide. Now, I'm going to take the liberty here and run these things on two screens, since I've got to compare stuff that we have here with each other. Okay, so here we go. This is basically where we are on this thing, and of course we're coming up here with our old friends, the spinners. So the spinner components are Kleps-Gordon coefficients. It's a very important piece of information because this doesn't stop with 2. As I showed you, you've got quadrupoles to be made if I've got 3 states. And then you've got octupoles to be made if I've got 4, and so on. This doesn't stop. This goes on forever. So you have to realize that while we're dealing with this, either looking at this thing in a circular polarization basis, where you have these imaginary numbers, or just looking at it where you hide the numbers on the matrices, just put them all on the C or Y type sigma, and then you've got 3 matrices that everyone knows and loves at this point. These look a little suspicious, but they're the same darn thing. You can see if I phase them correctly, the only difference is an overall factor of 1 over the square root of 2 for sigma, or the square root of 2 for j, x, y, and z respectively. So there's the circular type tensor notation up on top there. There's the stuff we're used to, good old Cartesian, x, y, and z, and there are the matrices that we know and love, right? Would it that we could get that familiar with what comes next? Now, remember that if I do use these guys, I get, and I do use them correctly, that is, if I take a representation matrix here, it will be our good old rotation matrix. Well, not quite. It's sort of got a reflection, the whole thing multiplied by -1. But minor detail. This is the idea of having an irreducible representation of the angular momentum type doing the transformation of the 3 operators, tensor, really vector operators. When you do that, you finally get, if you look at the Cartesian components, exactly a rotation of an expectation value vector. Okay, so we've already looked at that too. So it's this that you may have to review as we go into this new world with U3 as the thing that's important, and the thing that's important here that's new, besides the vector and the scalar, is the quadrupole. Okay, but we've worked with that too. We did the top-down derivation of the quadrupole representations, and this is the expression in terms of Kleps-Gordon coefficients again. Now, that result right there is just a couple of steps away from what's called the Wigner-Eckart theorem. So in addition to Irep tensor building, I got a link for the Wigner-Eckart theorem. I'm going to skewer over that pretty fast today, but here's the basic idea. These tensor operators for J spin states, starting with J equal 1, compressed that result, and I'm going to put it over here on the other screen. This is where we really need the other screen. You can see that all of these matrices only take up one super diagonal these matrices here take up the first lower super diagonal, right? These guys, they're completely diagonal. And because they're completely diagonal, all of these three matrices commute with each other. But then these guys and these guys don't commute. These guys and these don't commute. Here I take the first upper diagonal up with a antisymmetric combination and a symmetric combination. And each of the vectors that are leaning over, so to speak, each of those components are orthogonal, or orthonormal actually. That makes this really powerful. These guys, you can see, that's orthogonal to that. Then finally, the top dog is just a 1 up in the upper right-hand corner, like this one right here is just a 1 in the lower corner. Okay, you see that? That's important to see. It's been happening here, but you really don't notice it when it's only 3, 2 by 2 matrix. But here, it really stands up. Okay, so this is all part of the Wigner-Eckert stuff, and this is a way to get it out there so that A, you can look at it and do it by hand, but B, you can program it. We got closed forming for everything we talk about here. Okay, so you might say young tableau, young schmableau, right? What do we need young tableau for? We got computers, right?
Dr. Harter, this is Wigner-Eckert. These are the spherical tensor terms for the addition of 2 spin-1 particles, right?
Exactly.
That's funny.
Using the coupling coefficient, the Klipsch-Gordon coupling
Yeah, yeah.
coefficient for spin 1, with spin 1. Okay? Now what we've got here is that whole pile of things compressed. This whole top row here, compress it. Upper corner, upper diagonal, diagonal, lower diagonal, lowest diagonal. Okay? So we don't take up as much room in the textbook that I wrote that would have been way too large if I read on every one of them, especially these right here. Here we're talking about looking at spin 3. Here's spin 2. Okay? Spin 2 makes a hexadecapole, right? This one can only make a quadrupole. Okay? Now that's leaving out spin 1/2. Do not leave out spin 1/2. That's the next thing here. Okay? This is 1/2. That's the spinners that we had before over here, right? All compressed, right? That's pretty trivial. But then 3/2. If 3/2 is not trivial. And 5/2, not trivial. So all of these guys are tabulated in the, and there's a link to that. I don't see it right here, but
Dr. Harter, just have a question on the notation. So
Sure.
Most of the textbooks on quantum mechanics, whenever they discuss the inner product involving a tensor operator,
right.
so between the bra and a kid, they put 2 lines, 2 parallel lines. Like, so what's the significance of that one? Like, does it
That's the
convey-
overall coefficient of the tensor operator.
Okay.
And it's called the reduced tensor matrix element. Okay? And we'll see that, actually, notation, if I'm not mistaken. I think it's coming up here.
Yeah.
But the basic idea then is you've got this guy and you've got this guy, but then you've got this thing right here that doesn't, this is not a function of your Z components, right? So the reduced matrix element just takes that, and that, and puts it with the 2 lines when they do a matrix element. It's the overall coefficient, which then usually involves radial integrals if it's atomic physics, right? That's the last thing you get, and also the hardest thing to get, right? Because usually you don't know what the radial functions are.
This is the 3J form, right?
Yes, that's absolutely right. Let's see if we can get some of those guys showing here.
There's your
Tensors applied
reduced.
to D and F fields.
Reduced term.
Here's your reduced matrix element.
Oh, okay.
Okay.
There.
So, sure, I've got this tensor, and I don't know why that suddenly got covered up, but let's go back and get it. There we are. So this is where I actually want to use this stuff to go ahead and calculate an atomic crystal field splitting of the d orbital, let's say. And I've got all of the and more numbers than I possibly need with this table right here. Okay? But what I'm looking at is I'm taking each one of these multiple functions. Remember we use x's for those, big x's, right? If it was a tensor operator, I would have used a t. If I'm using the most popular notation, I usually write these as v's. I'm just following the literature there. Okay, and then that v would show up right here. That's the overall coefficient of all of the possible matrix elements in a 5 by 5 matrix, right? They're all going to have that coefficient, and that's where your radial integrals. And this is discussed shortly afterwards in this particular link. So you can see precisely what that is there. But we're interested in answers up to an overall coefficient now. Okay, and so that's all going to come from these guys, which we've already got numbers for using the Clebsch-Gordon formulation that preceded this. So let's go ahead and look at where the numbers come. In this particular case, it's not too difficult. And it looks like something is hiding a piece of this right there. I didn't notice that when I put it together this morning. So this should be a T right here. This is the notation we used before we got into this business with the D. So here's what we had when we did our first look at a crystal field. And it was angular momentum x, y, and z to the fourth power there, but same idea. Okay, and then this is the actual matrix being pulled off of this, and it has a diagonal. This is the T4 matrix right here. I'm pulling off the diagonal. Okay, that's what I need right here. I need the x4 0 or the v4 0 with a 2/5 in front of it. That comes out to be this. Okay, there's the 1 times 2/5, so on. There's the same coefficient. There's a 4. This is over square root of 70. That's something that makes this thing go outside as well. But anyway, those numbers are proportional to those numbers. Okay, and then the rest of it, this is extreme here of 4. I just use this one right here and this one right here to get these two. I'm done. Now I just have to diagonalize that. That's not very hard to do. This is already diagonal, so I've already got those eigenvalues. I just have to figure out what these are. Okay? 2/5, 2/5, and then 2 off diagonal. Well, that's a B-type matrix, right? All I have to do is take half the sum, 2/5 plus 2, and 2 minus 2/5, right? And so when I do that, I get this right here. Okay, that's the thing written out without any fractions, and there are my. I still haven't gotten the actual eigenvalues there, but that's what you get for this thing, and that's displayed right there.
But BR, you just have an extra 10 in the corner.
Let's see if that's this right here and this one.
Good.
And then
The next
you
one.
do a permutation, slide these guys down and bring this guy up. So that's okay. As far as
Right down there, that 10
oh,
in the bottom
yes. You're right there. That's right.
And the other one too?
Yeah. This 10 has to go.
What about the other one? What about that one?
It's true.
That's got
That has
final
to go
10.
too, right?
Yeah. I was
This
up
was in the
late,
final series.
up late on this one. Yeah.
This was the
Yeah,
extra.
we got to get rid of this 10 is legit because it's balanced, but this one is these two have supposedly migrated to here. So the eigenvalues for that are 12 and minus 8, which are the same numbers that we have down here. So that means that there are only 2 levels, and there they are. Okay? Well, let's bring this guy up to speed. And he has, of course, the same arithmetic problems. There, that's the thing for that. And let's go on and take this a little bit further. Sixth rank tensor. Remember? We talked about how that made a really complicated rotor spectrum out of one that was already pretty complicated from the fourth rank. We're only talking about angular momentum 2, but let's talk about 3. Okay? That's the next set of matrices past this one, the one that's now hidden. There's the angular momentum 2, but now the angular momentum 3, we're going to use part of that. Okay? And I'll let you do the looking up here, but this is basically what we have. Remember, when we did the top-down thing, we didn't go this far. We didn't go and look at the cubics too closely. But x, y, z was a difference between 3 sub 2, plus or minus. That's one eigenvector that this is going to have. It's going to belong to A2U of the octahedral group. This is an octahedrally symmetric combination here. And I see another thing. I'm sorry. This is the fourth rank octahedrally symmetric rank. And this is the matrix that it comes out here. And this is the number 4 for this one. And the eigenvalues that come from it are using the same vectors as this. So the result that we get when we're all done with this is really quite remarkable. This is the effect of the fourth rank splitting. And most of the time, that's sufficient for figuring out the perovskite orbitals. But there'll be always a little bit of that in there too, which will move them around a little bit according to these numbers. But these numbers will be very much smaller than these numbers because the the reduced matrix element for this one will be smaller than the one for this one. This is what's going to make that happen. Okay, so here's our 6 minus 2 and minus 12. That other thing is giving us quite a different picture. The T1U moves up to be the highest. The T2U moves down to be the middle. And A2U stays with the same number if you scale it as the original fourth rank. Now, where did we do this? Where did we get a real incredible war between levels? I guess I didn't attach that. Let me go ahead and restart this real quickly here and click on where we did this. I should have gone ahead and added this as the last slide. And it should come up here fairly quickly. This is, assuming the thing will let me in.
Yeah, we haven't yet on that one.
We haven't tried that.
No.
We haven't
That one's
tried.
gold.
Oh, there it goes. There it goes.
Whoa.
Okay. This guy right here, okay, was made. The levels were made out of a fourth and a sixth rank. Okay. These guys, right? A linear combination of this and that one, pretty much. Yeah, that's very close to the sixth rank guy. But this is the one that's the main operator for our rotors, right? Our SF6 rotors. Also, our tetrahedral rotors. So both of these molecules pretty much go with that. And they might have a little bit of this, okay? If they have only a very, very tiny amount, they can already be completely different in the threefold region, like that. So it doesn't take much of this to kill all of the stuff that lives in the valley. Now everybody's got to move them up to the mountains. And that's what's happening with angular momentum. We were doing 30, right? Well, here we're dealing with just 3, angular momentum 3. And you can see, definitely those levels are very different. But this was a whole forest of levels, right? Going through weird sort of avoided crossings and things. And this is something we can do with rotors. Can't do it with atoms, because in a crystalline field, the J is not a good quantum number. So a lot more happens to this. This is much more susceptible to having these tensors mixed. This one, angular momentum J, is the same for all of these surfaces. So we get to play incredible quantum mechanics with the levels that you're seeing when you run this thing here with a variable coefficient for that thing. This is what you're seeing. Now we'll unzoom this because the bottom is where we looked before. We looked right down here where we had these two full clusters, full of, this one had two T1s, a T2, an E, an A1. This one replaced the 1s by 2s, and you actually see the splittings. Then here, remember we did this one in color so you could see what they were all doing. Okay, so those are two extremes use of group theory to talk about angular momentum and the octahedral or tetrahedral symmetry. And we got to do more of that to really understand, because the nuclear spins haven't been mentioned yet in this problem. This one has 64 of those spin states because it's 2 to the 6th power. This one not so bad. It's only 2 to the 4th power.
So 16.
Nice 16, sweet 16. Okay, so this is one we can look at fairly easily. This is getting difficult.
And that has to be because 6.
What about this one?
Holy crap.
This is 6. This is 60. You say, oh, that's 30 times much. That's going to be hard. No. The 60's in the exponent. This is 1.5 octillion spin states. That's what we're going to be dealing with if we ever get to see the
Did you say
spectrum.
octillion states?
Octillion, as in octopus.
That's the molecule.
Remember the James Bond movie, Octopussy? That's what we're going to be dealing with.
Rather complicated.
This is already amazing. And this spectrum has been seen in detail.
How about the spin terms experimentally? Have they
That's
been?
what I'm talking about. Jacques Bourdais, right? That's the guy. He did it. Cost the French government $20 million. And they thought they were going to get separated uranium.
The Grail.
Jacques was not interested in separating uranium. He got this beautiful spectrum, closed shop. He had a whole factory with a CO2 cavity that was 30 meters long. I think that's the thing. I mean, it took up a whole... University of Paris 17, which is in kind of an industrial district of Paris, and there are a lot of factories that aren't doing anything. So he took over the thing and put this infrared spectrometer, and then taped it so that the magnetic field was kept out. And now he had no Doppler shift because he had these plane waves crossing each other really plain, because he had mirrors that were this big. And that's what it took to get the spectra of that we're sort of hiding in all of these things right here.
Experimentalist wet dream.
Yeah, it was amazing. I mean, French are known for spectroscopy, and this just pushed them to a new height. We're going to do everything differently now. We can't afford that kind of stuff. June Rui is going to do it with frequency combs, and we're going to figure out how to get so you have a single molecule. And you control the Doppler shift very nicely when
Going
you
to
do that.
town on it.
Yeah. If you can do that. Now that's the question. Now the real thing is we're going to take the baby steps. I'm saying start out looking at Freon 14, which is this. It's a gas. It's not going to react with your optics. It's not going to do anything nasty. Or you can use this one. This one likes to be a liquid, but the thing about this one, it doesn't even want. It's a gas. This one is, very harmless. It's in every transformer that you see those boxes up on the telephone poles. It's SF6. It's very stable. Okay, and it has a nice vapor pressure, so you get some molecules pretty easily. All right. This guy, not well behaved. This one wants to be a solid, but he's too big to really do it at first, and that's why we get to see the crazy guy. You just boil graphene using ultraviolet light.
How do you create that
There's several
molecule?
ways.
It's a really long story on how that is totally by accident. Basically, you just put two graphite rods together and run a DC current through it. That's
Vacated.
called an arc lamp. Okay, so you have an arc lamp in an argon vacuum.
And that creates that molecule.
It creates itself.
And a bunch of other fullerenes at the same time.
Yeah, it does. It does. C60 and C70 are majority. Then there's,
Have
as
you
he says,
studied-
quite a
have you-
number of
Have you
others.
studied the topological properties of it?
Come join us.
That's
Oh,
the
it's-
one that really looks like an American football. This one looks like a European football, right?
Yeah, that's right.
Yeah,
They
or
were-
South American, right?
Mhm.
They all have, they either TH symmetry or they're icosahedral, right?
Yeah, that just
D5.
there it is. That's
But
that.
yeah, there's your buckyball typical seams.
Well, they like these football players. They were kicking that thing, and they didn't know they had like a pokeball symmetry on that. Like,
right.
damn.
Nope. Yeah. And the newer soccer balls are TH. Remember I showed you TH? You know, it's where you take 3 cards, right? Run them through each other, and then the third one perpendicular. And if the cards are golden rectangle ratios, the points on the cards all make an icosahedron.
So I guess if you shrink the pentagons, it breaks the icosahedral symmetry. Isn't that correct? It breaks it down to the TH you were talking about.
If you shrink the cards, one
Just
aspect.
the pentagons.
Yeah, yeah. If you deviate from golden ratio card, then you're TH without being icosahedral. But you're close, and that's what happens. This molecule
But it is
would
true as well.
at low temperatures would, I think, prefer to make a TH lattice. But I'm not sure about that. That's something that remains to be seen. Because when they do make Buckminster fullerite, which is the crystal, it's got the color of root beer. I think I even have some of it left over from when the heyday of this molecule. The basic idea is that here's this solid fullerite, but every one of those, at room temperature, every one of those molecules is rotating in all 3 directions. It's a bunch of ball bearings that are basically frictionless in all directions. So it's a crystalline lattice that has icosahedral symmetry, but until you cool it, it's in motion.
So
In other words, it
So-
really is icosahedral symmetry in a crystal, which everyone would say is possible, but this is a dynamic symmetry. They're all spheres sitting in basically face-centered cubic arrays.
And you mentioned formation, and he mentioned ball bearings. That's another technique. You just put a bunch of carbon in a vat and tumble it. And stainless steel bearings will, when they come together, the tumbling action is strong enough to break those bonds, and it comes back together in fullerenes. It's like a low tech way of doing it.
Well, the other way of handling it
Wait.
is you make a carbon arc again, but this time you put AC. You make the current oscillate. Then you get what are called bucky onions. And it's great big buckyballs. It starts to make the buckyball, then lays more carbon on top of the thing, and then another layer, and then another layer, and then until you have some of the electron micrographs show 100 layers.
Pokeballs.
But inside,
Fullerenes, yeah.
in a Russian doll, inside you have a buckyball, presumably at the center, although no one's really proved that. But then outside of that is something else that has the same sort of symmetry, but no one's really looked at that either. And so on, as you go out, then you start to see faces forming. And so you get this onion that has more or less icosahedral symmetry, but it's usually flawed symmetry, because, you know, it's just happening randomly. So the onion, which would, if it was, this was the side of buckyball, the onions get about that big. So they have to be looked at like electron micrograph, or something that really magnifies. But just as that was starting to get underway, then they started realizing that the Bucky tubes were really important.
Oh yeah.
So almost all the research went for the Bucky tubes.
And now graphene.
And the idea was that you could make incredibly, if you made them long, it'd be a really
Everyone
strong
is doing
material.
graphene.
But then they found that some of them were semiconductors, some of them were conductors, some of them were halfway in between, and it all depended on how the tubes formed, whether you did this, or this, or
Chirality.
this. So you had a chirality as you made the tubes, right? So you had weird kind of lattices that you were playing with. So people really got good at that, and then these guys, these Russians, discovered with Scotch tape you could produce graphene. That was the next fad, right? And that's still a fad. It's still going. But sometimes all this stuff's going to sort of die down. We got to go back and look at this thing. This is what started it all. So
Dr. Harter,
there's a
graphene.
lot left to be done.
So is graphene? Is it a molecule or what in terms of its classification?
It's a two-dimensional solid, but solid is used loosely. It is it starts out anyway. That's the thing that the guy got the Nobel Prize for, was actually doing it so that he produced a single layer of hexagonally laid out. I mean, it was a hexagonal lattice that is called graphene.
Right.
Okay, and had those funny Dirac bands,
That's right.
right? The Dirac points, conical intersections.
So is there an upper limit, like how many atoms you could have to call something a molecule, and if it exceeds certain number of atoms, then you call it?
Really good question, because to me that's the way to analyze solids, is to start with a unit cell, even though it's not stable, right? But you can make it stable on a computer or on paper.
Yeah, because
and that's a molecule, right? You could say, oh, I'm only allowed to rotate in a plane, so, you know, that's a pretty easy angular momentum problem, right? And so then you have you ask, what is the spectrum of this thing when it's rotating and vibrating? That would be a simple vibrotor. Your electrons aren't doing anything, they're just bonding, and they're adiabatically following the vibration easily, but the rotation even more easily, right? If it's a stable bunch of bonds, okay? And so then you just say, okay, once I understand that, I'm going to put one more layer on, right? Well, all that's going to happen is the bands that you really are looking for are going to get a couple more dots on, right? And you keep putting more and more on, and you get but you also are doing the thing, it's a topological solid. You've got the topology right. You aren't forcing the thing to sit in a rectangle that it doesn't want to sit in.
Catch that, Louis?
You see?
Bending the graphene around.
Yeah. So you're closing the boundary. You see? You're getting the beautiful kind of physics that we get because this is closed.
So fullerene is a solid, right? Is it?
Well, a solid is harder because you could start with a unit cell of a three-dimensional solid, right? And just call that a molecule, right? And then you can even imagine somehow you'd have to put something in there. You know the diamond is not stable. If you just make a tetrahedron of carbons by themselves, okay, it's gone in
Dr.
milliseconds.
Harter?
It's not stable.
Are Bucky onions solids?
I don't know about that.